All right. Hi, students. It's nice to be back with you guys. This is chapter 5, the math of getting around Euler circuits. So it all began with a fun kind of just puzzle that it was called I'm not sure if I'm saying this word, the Königsberg bridges puzzle. Sorry, I'm saying that wrong. Can you walk around town? So the question was, notice if you look at this, if you look at this map, okay. If we look at this map, and let me just see if I can scroll in on this. Okay. The question was, there was a town, I guess, called Königsberg, and the question was, can you walk around the town? So you see my little pointer in the top left corner of this picture. Can you walk around the town and go across every single bridge once and only once? So that's the question. So I can try again. I think I failed right then at that. But can I go over, okay, go over this bridge, then go over this bridge, go over this bridge. Okay, now I can come over here, go over this bridge, go over this bridge. Uh-oh, now I can't go back this way. Well, yeah, I can. I could go this way, then this way, this way, this way, this way. I think I almost did it. Anyways, the question is, that's just a puzzle, it's just fun. They would be like, okay, well, can I go and visit all the different islands of the city area and cross all these bridges once and only once? That's the question. And you can't skip any bridges. You have to cross every single one, but you can't go twice on a bridge. So that was a question. And this is called, this is a question that it sparked a whole area of mathematics, now known as graph theory. So I'll fill this blank in for you. If you haven't downloaded the notes, they should be in a link below this video. So what he did is he simplified this problem. And he just said, well, I don't need all these little buildings or all these little roads. I don't need that information. What's the most important things are the bridges and the different locations we need to go to, So he kind of simplified this drawing and made like a simpler just model of it. So they said he kind of wrote it as this is R. That's location. I mean, this is like the right, maybe, I don't know what the R stands for, maybe the right bank of the river. I'm not sure. And then you have an L on this side. So they said, okay, we'll put an R here. That's like one location. And then put an L on the other side. And then, there's four different islands. So these are the spots that you want to go to around the city, the destinations. And then you see there's another, there's two other bridges over here. Let me get there's a bridge here and there's a bridge here. So what we can do is we can just, the important places that we need to go, I made letters and circles to represent each of the different islands and the different locations. Now, for each bridge that connects I'm going to draw a bridge on my picture where the real bridges are connecting. So there's a bridge here from island B to island R. So I can do a line from B to R to kind of and simplify this. And then there's a bridge from B to D. So Now I can do from B to D on my little simple drawing. Okay, then there's from R to A, there's a bridge. So I can go from R to A here. And then there's a bridge from A to C, so I can do this. And then there's from C back to L, so C to L. But then there's also another bridge here going from C to L, a second bridge. So here I can do this one like this. And then I can do from, there's one from D to L, so I can go from here to here. And there's one that connecting D and C, so from here and here. And then the two bridges that I don't think we have done are these two bridges on the outsides. So there's a bridge on the left side of our picture that is connecting L to R. So I'm going to make a big like this. And there's another one over here on this side to connect R to L, and that's another one over here. Okay, so this picture it's kind of a model showing the most important parts of this more detailed picture above. So maybe mine is not as pretty. I think what might be even easier than redrawing it like I have done is maybe if I get a thick marker and draw it right on the actual picture and imagine us just erasing all of those details, like I said, the roads, the little ship, the river. We don't need all that information. If we're really just trying to figure out this problem, the most important information is the islands we're trying to get to and the bridges. So I'll try drawing this model. So the model I drew down here is the model of, but let me try a second time. And this time I want to do it with, I'm going to try to make a thicker pin line and maybe a darker color. So I would just draw a circle around each of these locations that you need to make it to. Those are the islands, and also the right bank and the left bank. I assume that's what that is. And then now I can just use the red and draw lines, connect where the bridges are, connecting the two islands, And then for these bridges over here, to the left and to the right, I can go from R all the way over here and then all the way over there, And then this one goes all the way over here to all the way over there. And then also, I don't know if I put this one, I think maybe I did. Yeah, and there's one more bridge. I didn't mark this one because I did these two. There's a bridge here. But I'm not going to draw it from here to here like it actually goes. I'm going to draw it from here to R because the final location is it's going to taking you to R, which is just the right side of the river, So I'm not going to draw this one. This bridge right here actually goes, this direction, but I'm going to draw it. All that it's important is where it connects, which 2 points it connects. It connects the right side of the river, which is by R, the top of the river, to the bottom of the river, to island B. So that's why I don't have to draw it going the same direction exactly. I just draw this bridge. I drew it right here, going straight up from B to R. So there's actually two bridges going between R and B. This one here and that one there, but I drew them both going in the same direction because it doesn't really matter. We'll see when we're doing this graph theory, it doesn't really matter. All right, so if you imagine now erasing all of the all the actual bridges and all of the river, the city, everything else, and just having the red and blue marks that I drew there and the letters like A, B, C, D, and L, R. That's what the model of this picture would actually look like. So it just to show you. And so I try to do it down here as well, but I think it looks much better actually on the picture. And if you could just imagine erasing, like I said, all the little details. And I mean all the streets, all the buildings, all the rivers, the bridges, everything else, just the red and blue marks that I wrote on top of the bridge. That is what the model would look like. Okay. Oh, one more thing I missed. There's one more bridge over here. And it goes from island C to the left bank of the river. So instead of going, it actually goes, like horizontal. But instead of doing that, I'm going to draw it straight, going straight down to L, because I need it to go. It's taking you to the left side of the. I guess to the right side of this left bank, but the main thing is it's taking you to the left side. So there we go. Now I believe I have all of the, I forgot one. Hold on, one more. There's a bridge in between C and D, and we can actually draw that just by drawing right on top of that bridge. Yep, and there we go. I now got all the bridges there. So that's what it looks like to model. The picture, sorry, that took me so long to do. Okay, so that's what, like I said, if we just took all the detail out and we just made a drawing of the bridges and where they connect to, then we would get this model, and we call this a model. And that's what we are dealing with in graph theory, is just this model looking thing, and it's just made of two elements. There we go. The basic elements of a graph, we saw the first graph, and the two basic elements of them are the different locations that we saw, the different islands that you could get to by the bridges. Those are called vertices. And one single location, like vertices is plural, many places. Like if you're talking about just one simple location, it's a vertex. Then a path from one location to another. So like one bridge that we saw in the other picture, that is called an edge in the graph. So we look back at this picture and and this model, especially the model, and it's just made of straight lines we call edges, and the dots with the letters in them, or circles with the letters in them, those are called vertices. And that's graph theory. Don't freak out, because maybe when I started talking about graphs, you started thinking about algebra 1 and about graphing a line and plotting points, all that. And we're not going to do any of that. This is going to be way easier than all of that. So don't freak out. Just take a deep breath. Okay. So list the vertices and edges of the picture above. So what were the vertices? They were the different islands that they had to travel to. So it was A, B, C, D, and then it was the right bank of the river and the left bank, so R and L. So those are the vertices, or they call this the vertex set. So it was A, B, C, D, R, and L. Usually we name each vertice with a letter, or sometimes they use numbers, but preferably letters in this textbook. We like to use letters. Then the edge list lists the edges in the picture. So the edges are bridges. They connect, each time a vertex is connected by a line, that's called an edge. So like we see that C and D, those two vertices are connected. So we would see by this red line, so we would say if there's an edge there, it's CD. That's the name, that's what we name the edge, is by the beginning letter and ending letter, but DC or CD, whichever one you'd like. So, and then there's one red line between A and C because so we call that edge AC and so on. So let me make sure I'm pointing out this with my pointer. So this line connecting CD, that is called edge CD. And this line connecting AC, that is edge AC, and so on. And so there's actually two edges that are connecting RB. That's fine. We're going to list RB twice. It's this edge and this edge, right? There's actually two lines connecting R and L. So we have an RL here and we have an RL on this side. So that's fine. We'll also list two of those. That's fine. It's just telling us there's two bridges there. So I'm just going to do it on the other page. You guys can get on the right page. So I'm going to list all the edges in this graph. Well, I'm going to start with AR. There's AC. Maybe I'll focus on everything that's connected to A. Okay, now then everything that's connected to C, then there's CL, there's CD, and there's a second CL. Then it's everything connected to C. Okay, then I move around to L. Is there anything else connected to L? There's LR, two LRs. And then there's LD. And then, so I'm just like listing every red line that I see in the picture, So there's LD and then there's, okay, so then everything connected to D, well, we already listed DC, but then there's BD or DB, however you want to say it. And then from B, there's two RBs. And then from the R, oh, and we already listed the ones that connected R and L. We already listed those. So we didn't have to list them again. So that was actually kind of challenging. All I did was list the red lines I saw in the picture, but that was pretty confusing because like but for me, I noticed that when I started listing the ones that were connected to R, it was like RL and RL on the other side here. So let me show you. Yeah, it was like RL in this direction and RL in that direction. But then when I came around and focused on L and everything connected to L, I was like, oh, should we list LR going this way as well? But no, like RL, like this bridge should be in this list only once, right? And I have it RB is, you actually see that LR is listed twice, but it's not because we're going from L to R and back from R to L. It's because we're going from L to R on the left side here, and you also have to go from L to R on the left. I'm sorry, this is the left side, and then there's the right side. So because of the two bridges, one over here and one over here, that's why we had to list the LR twice, if that makes sense. Okay. All right, let's move on. So at a very simple level, graph theory is all based on lines and which connect, destinations, which are drawn by circles with either labeled with numbers or letters. And then it's just lines connecting them. That's all the graph theory has. So I feel like once you start thinking about it, it's really not very hard. But anyways, okay, let's move on. But of course, everything is easy when you've been looking at it for a long time. So anyways, I promise you this is not hard. So the next thing is to just introduce you some more definitions. Adjacent. So especially we're talking about the vertices. Adjacent means any two vertices that are connected by an edge. It makes sense. There's a road between the two. So, you could just get from one to the other in one single edge, or I call it like a road. So like, let's see, like this example, like 1 and 3, they are adjacent because they're connected by one edge. While 1 and 4 are not adjacent because you had to take two edges to get. You could have either gone this way through 3, or you could have gone this way through 5, but there's not like a straight one edge that connects you from 1 to 4. So 1 and 4 are not adjacent, and then 1 and 3 are adjacent, and 3 and 4 are adjacent, 5 and 4 are adjacent, and 1 and 5 are adjacent. And the only ones that are not adjacent pretty much are the ones across from each other. This 3 and 5 are not adjacent, and 1 and 4 are not adjacent. So. All right. Then we already went over that. You saw this. The vertex set is just the set of all the vertices. It's just a list of all the vertices in the graph. And then something I wanted to introduce a definition to you, and that's the degree of a vertice. And that is the number of edges meeting at that vertice. So if we look at just this problem below us, it's not very interesting. Let's go back to the other problem. Well, I'll explain this in the next problem, though. And then odd and even. If a degree is okay, so we call a vertice either odd vertice or an even vertice based on the degree of, if the degree is odd, then you would call it an odd vertice. If the degree of the vertice is even, then you would call it a even vertice. And I'll show you an example of it. And then also isolated, when a vertice is isolated, that means no edges are connecting to that vertex. So an example is the picture that we see below here. See 2, there's no edges connecting it. So we couldn't get there. So it's isolated. It's isolated. All right, let's go and see an example that has these these definitions in them. Okay, so we have this picture, and it says, what are the vertices that are adjacent to X? So here's X. The ones that are adjacent to X are the ones that could take one edge straight to and get to. So those are just Y and A. And it says list the vertex set. So I could just list all the letters in the picture. A, X, Y, B, Z, and C, right? List the degree of each vertex. So now what I do is I go around and I just count the number of lines that I think of it that are coming out. So look at A here. How many lines are coming out of A? So I see 2, 1, 2. So A has a degree of 2. That vertice has a degree 2. And then I must do right DEG, the rest of them. And then the same thing with X, there's two going. And it's not really a direction, but I think of like how many ways could you get out of there? You know, how many roads would take me out of, if X were like a location, like how many roads would take me out? So there's two. So X has degree 2 as well, just like A. Then we look at B, location B, and we see if I wanted to get out of there, how many ways could I run? Well, I could run this way, or this way. So it has a degree 3. And then C, if I want to escape from C, then the only way I could go is this way. So this has degree 1. Y, I could go up. Now, something important here, you see how these lines cross? It doesn't actually mean that I can change direction there. There's not a meeting. There's not a vertex there. So it's like, think about freeways that one is going right underneath the other. I cannot get off this freeway and start going the other direction. They just go on top of each other. They don't connect. Okay. So Y, I can either go up and I could go straight to B, or I could go straight to X. Those are the two directions I can go from Y. But I cannot go like, oh, I stop right here in the middle and then start going that way. I can't do that. That's just basically that line. Let me show you. This line from A to Z, it might as well, you could have also done the same graph. It means the same thing if you would have drawn it on the outside of X and Y. And it would have mean the same thing. It just means that A and Z are connected. Okay. Now, so Y is degree 2. And then Z, this is interesting. Z has, it actually has a loop here. This is called a loop, where it comes out and it comes back in. And because of the loop, we actually get that's degree 2 already. And then because I could run this way, or I could run that way, or I could run this way, or I can run this way. So this actually, Z has degree 4. All right, so you have to note there, because it's a little bit confusing, that that this loop of around Z, it actually contributes 2, not 1, to the degree of point of vertex Z. So just note that. But anyway, so we saw all of the degrees. Next, it says list the odd vertices and the even vertices. So just all the ones that have, even numbers are 2, 4, 6, 8, 10, multiples of 2. So A is even. Even is A, X, Y, and Z. Okay. So those are the even vertices. Is A because it's 2 has a degree 2, and X has a degree 2, and Y has a degree 2, and Z has degree 4. So those are all, like even vertices, and then you have odd vertices. And it is all the ones that have odd number for degree. So that is C, because it has degree 1, and then that's B. And I believe, let me just count all of them to make sure that there's one, in part 2, we listed all the vertices. So 1, 2, 3, 4, 5, 6. If I got that right, then there's 1, 2, 3, 4 that are even and 1, 2 that are odd. So there you go. It looks like I did it right. And then they ask, are there any isolated points? So remember, an isolated point is like 2 here that there's no a way to get out of there. Basically, if you think about the edges as roads out, there's no way to get out of 2. So do we see anything like that going on with this graph? No, we don't. So there's no isolated points. All right, and then here, next, it says, we see a picture, we see 2 pictures. And we see, it says a blank graph is one in which all vertices can be reached from any other vertex on the graph. So there's a road to there's a road to every location. If you want to get to every location in the map, there is a road that can get you, there. You might have to take lots of roads to get there, but you can get there. So that's the picture here at the bottom. This is a connected graph here at the bottom. And this is a picture of what it looks like when they're disconnected, where obviously A, B, and C, you can get to those areas, but there's roads connecting those or edges connecting those, right? And then, but you can't get from B to D because there is no road. So this is what it looks like when and actually it's broken into 2 different parts because D and E, you could travel between D and E. That's like one part of the graph. And then you could travel between A, B, and C, and that's like the other part of the graph. So it's broken into 2 separate parts. There you go. So that's what a disconnected graph looks like and a connected graph. So let me write in the correct words here. So a connected graph is one in which all the vertices can be reached from any other vertex in the graph. And then the other one is a disconnected one. Oh, yeah, I already wrote the word graph. Is the one in which you can't reach every vertice from every other one. Okay. All right, then coming up next, we have some more definitions, and this is involving edges. So 2 edges are adjacent if they share the same vertex. A loop, we saw a loop in the previous problem. A loop is an edge that connects a vertex with itself. So sometimes that happens. And then there's multiple edges, and we saw that in our first example where you have like more than one bridge connecting 2 locations. And then edge list is just a list of all the edges, which you kind of did already in the first problem. And a bridge, this is a new definition. It's an edge in a connected graph that without which the graph would be disconnected. So let's go back to the previous part here, over here. See this green line in the connected graph? See this green line, the added edge in the connected graph? When I added that edge, so if you imagine having the disconnected graph, right? Once I add this edge, now it becomes a connected graph. So they call this edge, this has a special name. It's called a bridge. So forget about the previous definitions of bridge, but now we know what the definition of bridge means here in graph theory. Adding that, if you will, edge, or I like to call them roads as well. It makes it now that all the locations can be gotten to by any of the other locations. Okay. All right. The added edge in the connected bridge in the picture of the connected graph above is what? So the added edge that was a bridge is this edge CD. I know it. An edge is a bridge when I should really put the word if here. If when I take it away from the graph, then it becomes disconnected. So later on, we're going to be having to really think about which edges are bridges and which edges are not. You can always tell because if you take away a bridge, then it makes the graph disconnected. So, all right, then is this a connected graph or a disconnected graph? So we look at this now, we're looking at example 3 now, and we're looking at this picture. And is this a connected or a disconnected graph? Well, it looks like there's no like points that we can't get to by one of these, if you want to call these roads. There's 1, 2, 3, 4, 5, 6, and it looks like I can get to any one of these places via one of these roads, right? So like if I want to get to 6 from 1, I could go from here to here, then from here to here, then here to here. So basically there's a lot black lines connecting to get to every single location here. So this is a connected graph. There's no, and I mean, there's nobody's isolated or no few are isolated, right? Oh, it's a connected graph. I guess the correct answer would be connected. Okay. Are there any loops? If so, where? Yes, there's a loop. It leaves a vertex and it doubles back on itself and it comes straight to that same vertex again. So yes, there is a loop at 6. Are there multiple edges in this graph? If so, where? Yes, notice how between the vertices of 2 and 3, there's 2 lines. So that means that there's 2 different ways, or if you want, 2 bridges that connect 2 and 3 together. So we would be listing those twice. So yes, between 2 and 3. And also, if you look at 5 and 1, there's actually 3 roads. They look good for you if there's heavy traffic on it, and then there's 3 different ways to get there, right? So that's great. So, and between one and 5. What edges are adjacent to edge? What edges are adjacent to edge that connects 3, 4? So here's 3, 4 is right here. What are the edges adjacent to that? Well, that means like next to 3, this line. So there's this line, and this line, and these lines, I guess, too. So basically, any line that connects to 3 or 4 is also going to be adjacent to line 3, 4. Okay, so we can list them all. And I wish this graph had letter names instead of number names because it's a little bit hard. It's harder to list. I'm not gonna list the ones that are adjacent. I just pointed them out. It's this edge between 3 and 6, between 3 and 5, the 2 between 3 and 2, and the 1 between 2 and 4. They're all adjacent to this edge 3, 4. Okay. Are there any bridges? So let's go around the graph and let's take off an edge and ask ourselves, can we still get to all the locations? So if like I take off the edge here between 1 and 2, can I still get from 2 to 1 if I really want to go there? Well, yeah, I would go up to 3, then over to 5 and down to 1, but it would take me longer, but I could still get from 2 to 1, right? And I could still get everywhere around to all the other vertices. So this is not a bridge. In fact, there's 3 ways to get from 1 to 5, so none of these are bridges. In fact, if I took all of those off, I could still get from 1 to 5 by going through 2, going around. I'd go from 1 to 2 to 3 to 5, so I could still get to 5. So none of these are bridges. I mean, this one is not a bridge either. I keep putting my finger over it and imagining that that edge is not there and asking, can I still get to every vertice? And the only one that really looks like a problem is possibly this one that connects 3 and 6. Because if I take that one away, that's the only route to 6. It looks like when I look at it, all the other vertices, like 1, there's multiple ways to get to 1. There's 1, 2, 3 ways to get from 5 to 1. And then there's 1 way from 2 to get to 1. So there's plenty of ways that I can get to 1. So I don't think any of these ones around 1 are going to be a bridge. The same thing with 5. There's multiple ways to get to 5. If I took any of them away, I think I'd still be able to get to 5. And the same with 3, and the same with 2, and the same with 4. But the only one that we have a vertex here that there's only one way to get to it. And that is by way of 3, or by way of itself, which still, if well, that one kind of sort of doesn't count when we're talking about bridge, right? Because if I take this away from 3 to 6, I mean, 6 can be connected to itself, but it would not be connected to anything else in the graph. So the only bridge I see here is from 3 to 6. So it's the edge that connects 3 to 6. Normally I would have called it 3, 6, but then it looks like 36, but. All right, so now here we have some more definitions coming your way. A path here at the bottom well, I'll let you read the scientific and the more exact definition of it, if you will, but I'm going to define, and just to say in layman's terms, a path is a route that gets you from one vertex to another without retracing your steps. So it's like, and it's okay to go back to the same vertex on a path. If you're on a path somewhere, so for some reason you pass the same location, it's okay, but you can't go on the same road, because going on the same road would be extra time and extra effort and extra gas. So a path is it just like it sounds. It's a route from one vertex to another, and as you can't retrace your steps, or we can't go on the same bridge twice. But it's okay to go to the same vertex twice. And another thing that I didn't write down here, I emphasize with a path starts in one place and ends in another place. So like if you were going on a hike, you wouldn't want to go take a path in a sense of this term, because like you usually like to hike like kind of in a circular thing where you come back to your car, because usually park your car, then you like go on a hike, and then you would want to circle back and get back to your car. So with this type of path, it's just from A to B, and then you wouldn't come back, like so. The circuit is a path that is a loop. Not a loop in the sense that we were saying loop a minute ago in the definition here, but I mean circle. It's a circle. This would be something that if you were going on a hike, you could go follow the path, and then it's kind of like would take you back to your car again. You'd start at your car, you go all the way around and come back to your car. So that's what a circuit is, hence the word circ. Just like a circ, you see the word circ and circle, and just like you see the word circ and circular. So that circ is a Latin word for ring. So that's why we see circuit is a circular path that begins and it ends in the same spot. And then the length is the number of edges in a path or a circuit. All right, so use the following graph to answer the questions below. Find a path from A to B passing through Y. So I could go like this. I could go to X, then to Y. Oops. Ooh. Not sure how I got that circle in there. I said maybe it's a circle. I don't know. From X to Y, and then I could go from Y. I'm sorry, I could go from A, starting at A, I could go from A to X, then X to Y, then Y to B. So some say that you take edge A, B, A, X first, then you take X, Y next, and then you take B, Y, and that's the way we describe that path. But another shortcut is just listing the vertices you go to in order. So you could list the edges like I did right here to describe the path, but it was also just fine if you want to just list the vertices. I started at A, I went to X, and then I went to Y, and then I went to B, right? 1, 2, 3, 4. So there's 4 different locations that we went to. But how many edges did I have to travel on? 1, 2, 3. So we actually took 3 roads, if you will, to get to which I'm calling roads the same as edges. I'm kind of just using those words interchangeably. Hopefully that helps you. Anyways, so I would say that's of length 3. Because we just saw in the definition that it's the number of edges that you cross in that path or circuit. So it says find a path from A to B and state the length. So there's another way to get from A to B. I could go from A and then go to Z and then go to B. So that would be, I would describe that. You could, like I said, I would do A, Z, B. That's how I would describe that path. And the length is also 3. Oh, 2. Length 2. So that's a little faster if you're concerned about the number of roads you had to go on, right? And then it says, find a circuit that starts at A. So a circuit is a circular path, right? So I could start at A, I could go to X, Y, B, then go to Z and come back to A. So see how I came back to my starting place? So then I could name it A, X, Y, from Y I went to B, from B I went to Z, and from Z I went back to A. So that's the circuit. Some interesting things about a circuit. They call A here the starting spot, but really it would have been the same circuit. I mean, I would be describing the same circuit if I started at X and went Y, B, Z, A, X and ended at X. It would be describing the same circuit, right? So it's kind of like we don't even really say that there's a starting place of a circuit. They just would describe the ones that you go through to I guess the vertices you go to go to this circuit. I guess that's how you could do it, but it says find a different circuit that starts with A. So Like I said, we can't do this. That would be wrong because this is not, remember, those are not, we can't do that. You can't, those are like freeways going under each other. You cannot stop and go from that freeway to the next freeway. You can't do that, okay? But what we could do, I guess, is just go the opposite direction. We could go C, Z, B, Y, X, A. And normally, I don't even think that's a good question. Is that a different circuit? And I don't even think that's a different circuit. It's just the other direction of the same circuit. So I don't think it matters which direction you go or which part you start at. I think they're just, think of that as the same circuit, really. I mean, just rewrite the name in a different way. So we could have called that a Z B Y X A, which is exactly like the opposite, right, of these letters. But they're not really, so I guess there's not really a different circuit for that. It's just going the opposite direction. Okay. Now, some important definitions are an Euler path. An Euler path is a path that covers all of the edges in the graph. That's back to our problem that we were talking about. Can we go through all the bridges once and only once, right? So that's an Euler path. Would go through a path. You have to go on it once and only once, on each edge once and only once. But then we added the fact that all the edges of the graph we go over. So that's when we add that requirement, we went over all the edges. Then it's an Euler path. So in an Euler path, like I said, you go through all the edges of the graph once and only once. And you don't have to have your starting place be the same as your ending place. Then an Euler circuit is a circuit that covers all the edges of the graph. So it starts in one spot, goes all through the edge of the graph once and only once, and then comes back exactly to where it started. That's an Euler circuit. So you can stop the video right there if you'd like to, but I'm just going to go ahead and do this next example. Wait, oh, you know what? There's another example here, and I'm going to just go ahead and do this as review. If you want to stop the video, and if you want to just keep going on, you can, but I'm going to do this next example as extra review. It says, use the following graph to answer the questions below. Is this a connected or disconnected graph? So I don't see any points that are isolated or any parts of the graph that are isolated. I can get anywhere I want. There's a road connecting E, right? It looks like a little scary at E, but even if I was at D, I could go from D to A, H, G, F, and get to E. So it looks like I can get anywhere I want around. I can go to any vertex I want. So it's connected. Find a path starting at H and ending at F. So starting at H, and where's F at? Oh, F right there. Okay, so I can go straight there, H to F. That's a path. And there was only one edge, so it's one in length. The number 1 in length. Says find a different path at H and ending at F. So I could have gone from H to G to F, right? But you're thinking, why would anybody do that, right? And then that would be of length 2, because I went from here to here, that was 1, and I went from here to here, that was 2. So that's length 2. Even that, and it's a little bit confusing because you see 3 letters. But the length is, if you list the letters as one letter at a time and not the edges, then the length is not equal to the letters listed here. So anyways, can you find another path starting at H and ending in F? If so, state the length. So can I find another path starting at H that goes to F? Now, if I go this way, careful. Wait, okay, so I could go this way. I mean, I already went this way, I already went up, and I already went down. So those are all taken care of, right? I guess another path that I didn't like list here, one of the more obvious ones, is I could go from H to G. I didn't actually exhaust all of the paths. I could go H to G, and I could do this scenic route of going around G, and then I could go back to, and I could go around from G to F. So another one would be, and I think we list this as H, G, and then back to G, and then back to F. So that would be of length 4. And then another one would be if let's see if there's any ones that come from going this way. So if I go this way to A, and then I go around to D, and then I go down to B, and then come back to A. Now, remember, for this to be a circuit or a path, I cannot go on the same road twice. So I went on from A to H, and then I went from A to D, then D to B, and then B to A. I went on every road once. But then look what happens. I have to go on this road, AH, a second time. So that won't work. Let me see if I can show you again with my pointer. So if I start here and I go across, and I'm trying to just find a different route to go from H to F. So I go here, I go here, I go around here. Everything's okay because I remember at the path and a circuit, I have to drive on every road once and only once. But as soon as I get past here, I hit A, I come back to A. There's no problem. I can hit the same vertice twice. But because I already went on this road AH, I can't go on that road AH again. So that means that this would not be a path anymore. So it looks like the only other path, and I mean, it looks like no matter what, as soon as I cross AH, it's like I burn that bridge. So if I come moving and traveling around here, I can't go back over there because I've already used that bridge, right? So no matter what combination of going to C, D, B, or D, B, or whatever I do over here, I'm not going to be able to get back to F because I already traveled on AH. So it looks to me that this is the only other path that we can go from H to F. All right, then they ask us, is there any bridges? Now remember, I like to like go around and like imagine erasing. I put my finger over certain, what if this one's gone? Could I get from D to C to B to everywhere else? Yeah, I could. What if this one's gone? Of course, I could go from D, instead of going from D to A, I could go from D to B to A, right? What if this one's gone? Could I get to C still? Yeah, I could go to D to C, B to C. I could still there's a road to get to everything so far. If I take that away, I could just go, if I was at B, I'd go to D, it's back to A. Same thing if I took that away, right, or that. It looks like everything, okay, except for EF. If I took EF off, EF is the only road going to E, so that would be a bridge. And then the same thing with AH, right? If AH was taken off, and we kind of saw that already before, that then there would be no way from getting to the vertices from EF, GH, there'd be no way to get over to DCB, right? So AH is also a bridge. And it doesn't look like there's, I mean, as we look around this area, I mean, if I erase that, I can still get from G to H, just going the other direction this way. So it looks like there's always, another way to, I mean, I like to erase, to find a bridge, I like to go around erasing or imagining that certain edges are erased and see if I can still get to everything. And if I can't, then I call it a bridge. But if also another way of doing it is finding like where there's only one connection, finding between like E, there's only one road leading out of E. There's only one road leading from A to H. But there's more roads going from F, H, HF, and HG, but I just there's only one way across. So it literally looks like a bridge, Okay. Anyways, it says identify any loops. There's a loop at G. I wouldn't say G is loop, G is at vertice. There's a loop at G. And they say list the vertex set. The vertex set is A is all of the locations there, A, B, C, D, E, F, G, H. Give the edge list. Oh my gosh, this is going to be a long time. So I'm almost going to use a different color. And as I color each edge, then I'm going to write it down so I know it's DB. This is hard to do. Then DC, CB, then DA, AB, then AH, then EHF, then HG, then this is interesting, GG is the loop, then GF, and then EF. And so I got all of them. I think that's a good way to do it if you want to print this page and use markers yourself, because for whatever reason, it's easy to get mixed up and you're trying to count how many, edges are there, but it's hard. So anyways, okay. Now that we did that, now I can erase this. Now they ask us find the degree of each vertex and write it on the graph below. And I'm going to write it on the graph above. I'm sorry, I meant above here. So I'll just do it in two. So degree, so I'm looking at A. So when I think of degree, I think of if I was at A, how many routes of escape do I have? There's a bad guy trying to, hurt me. So I could go north, I could go south, or I can go east, right? So there's 3 routes of escape. So degree 3, vertice 3 has degree, vertice A has degree 3. And then now I move on to the next one, B. If I'm at B, how many routes of escape do I have? I have 1, 2, 3. So it has 3 as well. Okay, and then vertice C, it's up or down, so it's 2. Then D, it's to the right, down, or to the left, so it's 3. E is, I could just go to the right, so it's just 1. F is 1, 2, 3. And G is a tricky one. So I could go to the left, I could go to the right, or I could go to the right way around the loop, or I could go to the left way around the loop. So the loop actually adds 2 to the degree. So it's 1, 2, 3, 4. And then they ask us, the next question they ask us is they say, find a circuit that begins at F and state the length. So if we're at F, I know a circuit. A circle is just, it's a path that happens to start at F and then end at F. So can start at F, go to H, then go to G, then go back to F. That's a circuit. And how many edges do I have to go on to go through that circuit? It was one edge from F to H, and then another edge from G to H, and then another edge from G to F. So it's 3. So I will write that down here. F, H, G, F. And I can't remember if they want you to, I think they do want you to list the F a second time. Just saying we end at F. And the length there is 3. And there we go. Oh, it says find a different circuit that begins with F, state the length. A different circuit. Oh, so I could see 2 that you could go F, and then you could go around this, and then you can go to H to F. So I would say that would just add a little extra length. Like I said, I don't think we could go like here, because we'd have to go back on the same route going same AH going back. So I don't think that would not be a circuit that we could think of. But the one is we go from F to G, then from G to itself back to G, because you go from F to G, then around from G to back to G, then you go from G to H, then H to F. So F to G, G back to G, then G to H, then H to F. And this one has, and I like to count it as I go around, so it has 1, 2, 3, 4 sides. So this is length 4. And then it says, find a circuit that begins at C. State the length. So it begins at C. I could go down to B, then go up to D and back to C. That's not the only one, right? But that's one. So I would say C, B, D, C. That's the circuit. And I have to count it carefully. 1, 2, 3. Length 3. And then it says find a different circuit that begins at C. So you could go this way. D, A, B. Oh, no, I'm sorry, you have to start at C. But I meant go that direction. But okay, so start at C, then go to D. And then A, B, back to C. So D, A, B, or C, D, A, B, then back to C. C, D, A, B. C, D, A, B, then back to C. And let's count the number that we go here. So C, so 1, 2, 3, 4. And there we go. All right, there's the review practice. Okay, so next, they want us to model. And like I said, we're just drawing all the roads and all the vertices. And we're just going to be, we're just going to be kind of thinking about all of the unnecessary details being gone and only the edges and dots, or with the edges and vertices to be left when we're done with the picture. So a night watchman must walk the streets of a neighborhood shown in the figure. A watchman needs to walk only once along each block. Draw a graph that models this street routing problem. So one thing I could draw a graph is see this for every point that he could change direction, I'm going to make it vertice. As he walks around this neighborhood. And then for each time that he can walk on that road, I'm going to draw one edge. And they said he's only allowed to walk to go one time. So I'm only going to put so I'm just going to draw a line between, down each road that he needs to travel. I'm assuming these are like houses or blocks of houses. And these are like blocks. Okay, I'm redrawing a little bigger. And just he needs to walk on every street. So that's why and only once. So that's why I'm only making one line on each street. And this is what our graph would look like. I think I connected I probably should have, but one way of doing that better is it would be just to draw the entire street and then draw the vertices on it afterwards. That would probably we need a vertice right here. I probably would have gone, I need to connect that right there. I kind of did this the long way and hard way, but that's okay. We got to the end. Okay. So if you wanted to take off now, only the blue lines that I drew, that is the model that we would use, as our graph theory model for that picture. The fact that these are a park, that doesn't matter, right? And so the same thing. So they ask us, so some problems are a little bit different. So let's look at this example 7. A mail carrier must walk the streets of a city subdivision shown in the following map. The mail carrier must make 2 passes on every block with houses on both sides of the street and 1 pass on the blocks that have houses on only one side of the street. Draw a graph that models this street routing problem. So we want to draw exactly what he has to walk. So if they say he has to go twice on that street, we're going to draw 2 lines on that street, 2 edges. So let me get a slightly thinner. So see, this post office, well, every corner, he's going to have a choice which way he wants to walk. So those are my vertices. Then, see, these, there's only houses on one side. So he only has to, I'm only gonna draw one line down there. Now, these houses, there's on both sides. So one side right here and one side here. Then one side here, one side here, one side here, one side here, if you will. This one only has one, so I'm gonna draw just one line. This has two houses on two sides, so I'm gonna draw two sides of the street again. And then this one, the same thing, two sides of the street, so two edges, and then just one side of the street right there. Then I'm gonna do one side of the street here, so one edge there, one edge here, one edge all the way, this one, one edge, because the post office is on the other side, and then two edges here, two edges here, two edges here, two edges here, one edge here, 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 and then two edges here, two edges here. Two edges here. Okay, I think I got all of them. But now if you imagine me erasing all the, like the post office, erase, oh wait, there's one street right there. Oops. No, you don't even have to, correction. This guy is trying to deliver mail. There's no streets on that. So we do not have to write a line there. You're only writing lines on where he must walk to deliver the mail. So even though there's an actual street in front of the post office, it's not of importance to us because we only want to draw the places that he has to walk. And so if you would imagine, I know in the picture they have all these little buildings and they have a post office. They erased all of that in the background and just have my blue markings, and then you would have the model that we need to be focused on. And I believe in the textbook, you can look at for examples where they actually kind of redraw all my blue drawings on the side. Let me see if I could lasso all my blue drawings. I might be able to just pick them up and move them. Okay, look there. That's what the actual model should look like. And so let me do this too. If you just picked up all of my blue drawings and if you just move them, that's what the model would look like. So there you go. Sometimes it helps just drawing it on the actual real picture anyways, but oh, I think if you're looking at that, I think I missed something. If I lasso it back over, hold on 1 second. Sorry, I have a road here. I have a road here. I have a road here, or two roads here because there's two sides of the street. That's right. But then I should have had two sides of the street right here. So I think I need two right here. So I actually missed something. Sorry about that. I'm just double checking because that's a double street. That's a single street, single street, single street, single street, single street. No houses here. Double street, double streets, double streets, single street here. Oh, wait, I forgot another one. There's double streets right here. I'm glad I picked up my picture and saw it a little bit better, but oh, and then there's double streets here as well. Right? That's First Street, Second Street, Third Street. So that was right here. Yeah, and now it's looking pretty good. I think I got it. All right, but that's what your models look like. But they're just, if you just imagine just drawing all the places that the person needs to go. If they say two times, if they need to pass that street twice, then you need to draw two bridges or edges between those two vertices. And so there you go. And I hope you found this valuable. I hope it was clear to you. And like I said, don't stress out. This is nothing like the graphing that you've done in like Algebra 1 and other classes. This is completely different. And I think you're going to find that it's a lot easier. All right. Have a good day. Bye.